Hello everyone, welcome to Circuits and Network class. Today we are going to look into the Cauer Form 1. Now, you already know that these methods are carried out to synthesize the circuit. Z of S is given in this particular case and we have to find out the Cauer Form 1 of the circuit. That means we are developing the circuit and the Cauer Form 1 is given by inductors in series and capacitors in parallel. Okay, so you are having inductors in series and capacitors in parallel. Also, you have to note something that the inductor is coming first and then you are having the capacitor. So first you are having the inductor in series and then you are having the capacitor in parallel, and then again an inductor and then a capacitor, and it goes on. Now, the figure will be as such only if the polynomial Z of S is having the power of S greater at the numerator. Okay, that is the degree of the numerator should be greater than the degree of the denominator. So if you look at this particular problem, we can just solve this problem. You can see over here that at the numerator the degree of the polynomial is 5. The highest order of S is 5, and in the denominator the highest order of S is 4. So over here you can see that the degree of the numerator, it is greater than that of the denominator. So we can continue. So you are going to take the polynomial Z of S. You have the polynomial Z of S and you are going to do the continued division of this polynomial. So you have S raised to 4 plus 4S square plus 3. We are going to carry out the continued division to S raised to 5 plus 12S cube plus 16S. And what should we multiply this particular term? What should we multiply with S raised to 4 in order to obtain 2S raised to 5? You have to multiply 2s. So you have 2s raised to 5 plus 8s cube plus 6s, and you just subtract the whole thing. You're going to do the subtraction and here you're going to get 4s cube plus 10s. Again you take the divisor from this side. So you get s raised to 4 plus 4s square plus 3. And then again, what should you multiply with 4s cube in order to get s raised to 4? So if you situation, if you're having a doubt, you just divide s raised to 4. You divide s raised to 4 by 4s cube. Okay, that is, this s raised to 4 is being divided by 4s cube. And whatever you get the answer, that should be written over here. So here you can see this cube and this raised to 4 will get cancelled. So you have s by 4. So if you are multiplying it, you can see that you will be getting s raised to 4 plus 10 s square by 4. And you just carry out the subtraction. 10s raised to square by 4 means it is 5s square by 2 actually, right? So you're just going to do the subtraction and you'll be getting 3 by 2 s square plus 3. Again you carry out the continued division, 4s cube plus 10s. Again you want to know what you have to multiply the section with, so I'm just going to divide 4s cube by 3 by 2 s square. So I'm going to get 8 by 3 s. So I should take 8 by 3 s over here. So that will give me 4s cube plus 8s. And again I'm going to carry out the division. And I'm going to get 2s and 3 by 2 s square plus 3. Again you carry out the continued division. Okay, so I'm just going to complete this over here. 3 by 4s. So you can do it on your own. It's quite simple. Okay, you can do it on your own. You subtract it and you'll be getting 0. So this is your final answer. Now you can just look at these terms, the quotients. So I'll just change the color of my pen to make this part clear. Okay, you can just view the quotients that you have obtained over here. Okay, just look at the quotients that you have obtained in this particular section. You have how many quotients? You have 1, 2, 3, 4 and 5. Okay, now each of these quotients are representing each element in your Cauer form. And we already know that the numerator is greater than the denominator, that is the degree of the numerator is greater than the degree of the denominator. So it's going to start with an inductor. Okay, so the easy method to construct is, once you have done your partial fraction method, you just take it in the order. First element coefficient will be the inductor, then you have the capacitor. Next, inductor, then capacitor, and then inductor, capacitor. It goes on like that. So the coefficient of S will give you the value of the particular element. Okay, the coefficient of S will give you the value of the particular element. So here you are having 1, 2, 3, 3 inductors and 2 capacitors. So you can draw the circuit. You have 1, 2, 3, and how many capacitors? 2 capacitors. So that's 1 and 2. So here there is no capacitor, and that's it. Okay, and what's the value of the inductor? It's 2 Henry, 1 by 4 farad. Here it's 8 by 3 Henry. Here is 3 by 4 farad, and then here it's 2 by 3 Henry. Okay, so this is how you're going to construct the Cauer form 1 of a particular element. Now let's see how to do the Cauer form 1 in cases where the degree of the denominator will be greater than that of the degree of the numerator. Okay, let's see how to do such problems. Okay, so I'll just write down an example. I'll just change the color of my pen to the previous color. Okay, so we can just do one more problem where the degree of the denominator is greater. Okay, this problem I won't be completing it. You can just try and solve it. I'll just tell the steps and the basic thing that you need to know. Okay, so this is your polynomial. You need to find out the Cauer form 1 of this particular polynomial. You have to find out the Cauer form 1. How do you find out the Cauer form 1? Now, what you have to do is, again, you have to do the continued division method, but you can just see over here that the degree of the denominator, okay, the degree of the denominator, that is greater than that of the numerator. So, problem has arisen because for us, relating to the Cauer form 1, the degree of the numerator should always be greater. But over here, the degree of the denominator is greater. So, what you have to do? In such situations, you have to consider the admittance, or you have to consider y of s. What is y of s? Y of s is the inverse of z of s. Y of s is the inverse of z of s. And how do you find out the inverse? You just interchange the numerator and the denominator. So you have s raised to 5 plus 18 s cube plus 48s divided by 6 s raised to 4 plus 42 s square plus 48. Now, one thing that you have to note is that whenever the degree of the numerator is greater than that, when the degree of the denominator is greater than that of the numerator, there will be a change in the figure also. Okay. Now, I'll come to that after we just complete the continued division. Now, you can carry out the continued division as usual. Okay. So, how do you carry out the continued division? You're going to just take the continued division. I'll just write this down. You just carry out the continued division. How? What will be the value over here? You have s raised to 5 and here is 6 s raised to 4. So, it will be s by 6. Okay. You can just complete the continued division. Okay. So, I'll just write the values of all the answers. Okay. All the partial quotients answers, I'll just give it over here. These are big fractions. You can just convert it to decimal if you wish. Okay. On doing the continued division, these are the partial quotients or the quotients that you're going to get. Okay. These are the partial quotients. So you have 5 partial quotients. Now you need to construct the figure. Okay, now you need to construct the figure. How do you construct the figure? Now, you can just look at the elements, and we told that the degree of the denominator is greater than that of the numerator. Now, in Cauer form 1, I had mentioned that the circuit starts with a series inductor. That was the case when the numerator was greater than the denominator. Now, in this case, the denominator is greater than the numerator. So, we are going to start off with the parallel capacitor. Okay, your circuit is going to begin with the parallel capacitor, and then you have the inductor, and then you have the parallel capacitor, and then the inductor, and so on. Okay, and so on. So it's C1, L1, C2, etc. up to Ln and Cn. So this is going to be your circuit. So what will be your answers? What do these partial quotients represent? In the previous case, I'm just switching to the previous case. In the previous case, we saw that the figure was starting with an inductor. So your first quotient was an inductor L1. But now what is your first quotient going to be? It's going to be C1. Then it's going to be C2. Sorry, L1. I'm sorry, it's L1. And then you have C2. And this will be L2. And then finally you have C3. So how many capacitors? 3 capacitors and 2 inductors. So you can draw the figure. You have 1 capacitor, 1 inductor, 2 capacitor, 2 inductor, and then you have a third capacitor. You can just write down the values. It will be 1 by 6 farad. Here it will be 6 by 11 Henry. Here it's going to be 121 by 222 farad, and here is going to be this big number. Okay, yes. And then last you have 128 by 444 farad. So this is your Cauer form 1. Okay, so in this video also I'll just go through how to find out Cauer form 2. Okay, let's just see how we are going to do the Cauer form 2. I hope this is clear. You have to check whether the denominator is degree is greater or smaller. It is preferred that the denominator of the degree should be smaller. If it's not, then you should rotate, or you should take the inverse of the particular given function and then carry out the continued division. Now let's just check Cauer form 2. Okay, let's just go through Cauer form 2. I'll just again use the previous color pen. Okay, let's go to Cauer form 2. Okay, yes. So you have Cauer form 2. Now, for Cauer form 2, it's similar to Cauer form 1. The only difference is that the capacitors and inductor positions have been interchanged. In Cauer form 1, you had the inductors in series and capacitors in parallel, whereas in Cauer form 2, you're having the inductors in parallel and the capacitors in series. So this is L1, C1, this is 1, L1, C1, C2, L2, C3, then you have Cn, and then you have Ln. Now, again, we can just solve this using a problem. Okay, so we need to find the Cauer form 2 of the polynomial given over here, that is s raised to 4 plus 4s square plus 3 whole divided by, this is s, okay, whole divided by s cube plus 2s. Now, in the Cauer form 1, we had checked the degree of the polynomial, that is whether the numerator was greater or the denominator was greater. Now, in the Cauer form 2, you need to check in which part, that is in the numerator or the denominator, you are having a common s term. Okay, so in the numerator, you are not having any power of s, that is s is not common in the numerator. So I'll just write it as such. You're not getting s common. But in the denominator, you can see there is an s cube and there is a 2s. So if I want, I can take an s outside. So you have s square plus 2. So you have s into s square plus 2. Now, for the Cauer form 2, the standard form is that our denominator should be having an s as common, or in other words, the pole should be at 0. Okay? Or if you want in simple terms, the denominator, for the denominator, you should have s common. That is the standard form. If it is so, then you can follow the same figure. Okay? Right. Now, let's see. Again, you have to do the continued division. This was just for our information. Now, while doing solving the Cauer form 2, you have to take the powers of s in the increasing order. So now, while solving, we are going to take this particular polynomial. We are not going to take the one with s common. This was just for us to check how we have to draw the figure. Okay. So you are going to take it in the reverse order. You are going to take 2s first. You are going to write down 2s first, and then you are going to write s cube. Again, on the dividend part, you are going to write 3, and then the next power of s, that is s square, and then the highest power of s raised to 4. And now you carry out the continued division. Now, you are going to get confused on what you have to give as the answer over here. In such situations, what do? We just take a working column. You take 3 divided by 2s. Okay, so 3 divided by 2s, you cannot do anything further on this. So 3 divided by 2s, that is your answer over here. 3 by 2s. Next, you just do the multiplications. 3 plus, I think it's going to be 3 by 2 s square. You can just subtract. You can do the subtractions, and then you get on solving, you're going to get 5 by 2 s square plus s raised to 4, and you just carry out the continued division as normal. Okay, you just carry out the continued division as normal. Again, if you are having doubts, you can always do in your working column, that is 2s divided by 5 by 2 s square. So here the s is going to get cancelled, so you're going to get 4 by 5, and in the denominator it's going to be ns. So you have 4 by 5 s. And then you just continue doing this division. I'll just write down the partial quotients over here. You can just try it by yourself. And then you have 1 by 5s. Okay, so these are your partial quotients. You have 4 partial quotients. Now you can see over here that your figure is it's starting with a capacitor. Okay, it's going to start with a capacitor. So you have to take the first value, that will be your capacitor. But there's a small change. In the Cauer Form 1, we took the direct quotients of S. Over here, this particular value, it represents 1 by C1. Why C1? Because C1 is your first term. And the second term will represent 1 by L1. The third term will represent 1 by C2, and the last one will represent 1 by L2. So when you're drawing the figure, what will you start with? You'll start with a capacitor. How many capacitors are you having? 2 capacitors. So you have 2 capacitors and you are having 2 inductors. And what will be the values? 3 by 2 is equal to 1 by C1. So if you want C1, you have to reverse it. That will be 2 by 3 farad. Again, the inductor, you have to reverse it. 5 by 4 Henry. 2 by 25 farad. And last but not the least, 5 Henry. So this is your Cauer Form 2. Now, again, this part I'm just going to just mention it. You can do a problem on your own. You will just check one last problem where Z of S is equal to S into S raised to 4 plus 3S square plus 1 whole divided by 3S raised to 4 plus 4S square plus 1. Okay. Now, you can see over here, S is common on the numerator side. Okay. S is common at the numerator side. So what do you have to do? Again, as in the previous case, you have to take y of s. You have to take y of s and then do the continued division. You have to take y of s and then do the continued division. And then whatever answers you get, okay, you're going to get answers as such. You're going to start your figure with, what are you going to start it with? In the previous case, we removed this first capacitor, right? There was an inductor, we removed it. So similarly, over here, because S is common on the numerator side, you're going to start with the shunt inductor. So you are having the shunt inductor at the beginning, and then you are having the capacitor. And it goes on. Okay, so over here, when you're solving this particular problem, I'll just mention that you'll be getting 3 inductors and 2 capacitors. Okay, so yes, so what I've drawn is approximately correct over here. I'll just mention the value answers over here. It's 1 Henry, 1 farad, 1 Henry, 1 farad, and 1 Henry. Okay, so this is the answer for the question given above. You can just try and solve it. Okay, so these are the particular cases in the Cauer Form 1 for the LC network, Cauer Form 1 and Cauer Form 2 for the LC network. So in the next video, we can see the Cauer Form 1 and 2 of the RL network and also the Foster forms of the RL network. Okay, so thank you for watching the video. Please stay tuned. Thank you.